Our last section and our last application that we're going to talk about in this class for integrals is calculating regions between curves. So we have we've looked at finding the region between a curve y equals x, or sorry, y equals f of x and the x-axis. And what we want to do now is we want to look at, well, what do I do? How do I find the region of an area bounded by two curves? So let's consider two curves, two functions, y equals f of x and y equals g of x, where on the interval AB, f of x is greater than or equal to g of x. So f of x is my upper curve, g of x is my lower curve. Now the goal then is to find the region, the area of the shaded region, the area between the upper and the lower curve, bounded between those two curves, and the line x equals a and x equals b. Now, we start with, we'll start with integrating with respect to x. We will once again rely on that slice and sum strategy, where we're going to chop up our interval a to b into some pieces. Okay, we're going to take the Riemann sum approach. So I'm going to chop a, b into n subintervals, and for simplicity, we're going to do equal subintervals this time, although, hopefully you get by now that it's very easy to generalize to a more general type of partition. But for now, we'll take equal subintervals. And so the width of each subinterval is going to be delta x equals b minus a over n. Okay, and you can see here now, so I've chopped this in. I'm going to approximate my area by a bunch of these rectangles. Okay, on each subinterval, we're building a rectangle that extends from the lower curve to the upper curve. On the kth subinterval then, now obviously the width of each rectangle is b minus a over n. To find the height of this rectangle, what I'm going to do on each of the subintervals is I'm going to pick a point xk star that's somewhere inside that subinterval, and I'm going to evaluate f at that point. I'm going to evaluate g at that point. So the height of the kth rectangle would simply be the difference between f at xk star and g at xk star. So the area of the kth rectangle is f at xk star minus g at xk star times delta x. I have n of them. I'm going to add them together. And once again, I've approximated my area by a Riemann sum as follows. Sum from k equals 1 to n of the quantity f at xk star minus g at xk star times delta x. So that's my approximation. And once again, as the grid points increase, as I chop my interval into finer and finer pieces, and I do so in such a way that I drive the width of each subinterval to 0, which drives the number of subintervals to infinity, my Riemann sum becomes a definite integral, and I get the area of the region between two curves as follows. The integral, the area of the region bounded by f of x and g of x, with f greater than or equal to g on the interval AB, is given by the integral, the definite integral from a to b of f of x minus g of x dx. And that's it. Okay, that's it for the area between two curves. All right, let's do an example. We'll look at the following example, where now I have my upper curve curve. Well, so my two curves are f of x equals 5 minus x squared, and g of x equals x squared minus 3. Okay, I want the area of the region bounded by those two curves. Okay. In order to do that, I need to know what the region is. Okay. So what if I'm not told what A and what B are? I just want the area bounded by those two curves. Well, that means I need to, if I look at the graph of those, so if I were to stick those in my graphing calculator, I'd see that, okay, they intersect each other. And so I want the region between those 2 points of intersection. So I need to know what that is. So I need to set f of x equal to g of x to figure out what that region's going to be. So I have 8 equals 2x squared equals 4. And so if I take the square root, x must be plus and minus 2. Okay, so that means I want the integral from minus 2 to positive 2 of this region. Now I need to know which one is on top and which one is on bottom in that region. And I could, obviously doing that, graphically, you'd see that, this curve, 5 minus x squared is going to be on top. So I'm just looking at 5 minus x squared minus x squared minus 3 minus 2 to 2. 5 minus 3 is 2 minus negative x, so that's minus 2 x squared. Oh, I'm sorry, I messed that up. So 5 minus a minus 3, that's actually 8. Now you might notice something now going back to the graph. You might notice that this region is symmetrical, and it's symmetrical about the y-axis, isn't it? So that's going to be the integral from negative 2 to 2 is 2 times the integral from 0 to 2 of this thing. Two times the integral from 0 to 2. Find the antiderivative, evaluate it between 0 and 2. That's going to work out to be 64 thirds. Okay. And we notice how, again, that's easier than doing this integral. That symmetry simplified the problem for us. Okay, made it go a little bit faster. Okay, next example. We want to find the area of the region bounded by the graphs f of x equals negative x squared plus 3x plus 6, and g of x equals the absolute value of 2x. Once again, I need to find where these things are equal. So let's note that g of x, in order to do that, equals 2x for x greater than or equal to 0, and negative 2x for x less than 0. So if I look at my graph, I put these into my graphing calculator, say, you'd see that they're going to look like this. So I can chop this into two pieces. Okay, so you know the lower and the upper function, it's still the absolute value of 2x. But to do this, I'm going to chop it into two pieces. I'm going to chop it into the piece that's less than 0 and chop it into the piece that's greater than 0. And so for the piece that's less than 0, I need to solve x squared plus 3x plus 6 equals negative 2x. And for the piece that's greater than 0, I need negative x squared plus 3x plus 6 equal to positive 2x. All right, so that for this first piece, that's going to be negative x squared plus 5x plus 6 equals 0. Which is going to give us the following, okay, which says x is -1 or x is positive 6. Well, it's only this when x is this, right, is x less than 0. And so only x equals -1 is relevant. So the first part of my integral will be from -1 to 0. And I'm going to do f of x minus g of x on that part. Okay, and so that's going to work out to be negative x squared plus 5x plus 6, right? dx. And for the next part, subtract 2x, so I get, actually, I'll put everything over to this side, so I'm going to get 0 equals x squared minus x minus 6. And so that's going to give me -3 and x plus 2. So since, again, this is for x greater than 0 here, on this side, that means x equals 3 is the only point we care about. And so the next part is going to be the integral from 0 to 3 of negative x squared like so. And each of those is relatively straightforward to integrate. Right, so we do the antiderivative, apply the fundamental theorem, and I'll save us some time and just, that's going to work out to be 50/3. The next thing we're going to look at is those occasions when we want to integrate with respect to y. Okay, there are occasions when it's convenient to reverse the roles of x and y. For example, consider the region shown in this diagram, where now I still want to find the region bounded by two functions, but now the function is the functions in question are x in terms of y. So I have a left function x equals g of y, and a right function, x equals f of y, and I want to build an integral that way. And in those cases, we treat y as the independent variable, and the setup is the same. I'm going to chop up my my region into pieces. So let's suppose I've got two functions, x equals g of y, x equals f of y, where g of y is less than or equal to f of y, and I have a line y equals c and an upper line y equals d, and I want to find the region bounded by those. And so what I'm going to do is I'm going to chop the y interval now, c to d, into pieces. I'm going to chop that into subintervals, and I'm going to chop them into subintervals in such a way, we're going to do equal subintervals again. Well, now the length of each subinterval, if I have n of them, is going to be d delta y is d minus c over n. Looks very similar, and it is. And I'm going to do the same process as I did before. I'm going to chop into subintervals, and on each subinterval, I'm going to find a point yk star now, and that point yk star, I'm going to evaluate my my right function, right, my greater function f at yk star, and my other function g at yk star on each interval. I'm going to make a Riemann sum, f of yk star minus g of yk star times delta y. Now it's a Riemann sum in terms of in terms of y. And once again, same idea. If I drive delta y to 0, that's going to drive the number of subintervals to infinity, and that's going to turn that Riemann sum into a definite integral. So here we'll put this together in a definition. Area of a region between two curves, but now with respect to y. So I have f of y greater than or equal to g of y on the y interval now, c to d. The area of the region bounded by the graphs x equals f of y, x equals g of y equals c, and y equals d will be the integral from c to d of f of y minus g of y dy. Okay, so now we can look at an example. We want to find the area of the region bounded by the curves y equals x cubed, y equals x plus 6, and the x-axis. Okay, now I could set this up as an x integral, right? I could find it by integrating with respect to x, but to do that, I'd have to chop it into some pieces. All right, I'd have to chop it into pieces, because on one piece, from x equals -6 to x equals 0, the region is, the bounds are going to be the x-axis and the line x plus 6. So on that portion, the area would be the integral from -6 to 0 of x plus 6 minus 0 dx. And then the next piece, I'm going to run from x equals 0 to x equals 2. And I would have to, right, set x plus 6 and x cubed equal to each other and to figure out where that is. But on that piece, the upper curve is the line x plus 6, and the lower curve is the cubic x cubed. And so on that piece, that region is the integral from 0 to 2 of x plus 6 minus x cubed dx. So I could do it that way. Or I could look at it in the other direction. And in the other direction, my upper curve, my right curve, is going to be y cubed. So what I'm going to do in that direction my, just to walk through the mechanics here, right? We have y equals x cubed, y equals x plus 6, and the x axis, that's the region we're interested in. Well, to do it in the y direction, I have x equals the cubed root of y, x equals y minus 6 now. And looking at it that way, now the region runs from y, the x-axis, right? That's y equals 0. And so now if I set these two pieces equal to each other, I find that the upper limit is still going to be the same part, 8. So now I'm going to end up integrating. Instead of having to chop that area into two pieces, I can do it at once by integrating from 0 to 8. Of the right piece is y to the 1/3, the cubed root, minus y minus 6 dy, and I can do it that way. Okay, I treat it the same. There's nothing special, right? Variable of integration, it's a dummy variable. And so I would do the same rules I would before. So 3/4 y to the 4/3 minus y squared over 2 plus 6y, and all that evaluated between 0 and 8. That would work out to be 28. All right, so that's it for this. So that last example, just to kind of see how that pans out. All right, so that we're just chopping the region. Sometimes it's easier to integrate the other way. One more example in the chapter, but it's, I think it's fairly straightforward. The hardest part can be figuring out how to define the region, and that generally means, right, if you have two functions, we have to figure out where they intersect very often. But in any case, I'll let you look through that last example. That's it for this section. So that's it, and that's it for the course. So we'll see you next time. Good luck on your exams.